Assalamualaikum and welcome to lecture number 10. In this lecture we are going to discuss about the Z-transform. In the previous chapter we talked about the sampling of continuous time signal, down sampling, up sampling, and quantization. So you know that sampling a signal in time domain corresponds to the produces replicas of the original signal displaced at the integer multiple of the sampling frequency. So there we use the Fourier. So Fourier is one of the analyzing tools for signals and system. In this chapter we are going to talk about another analyzing and useful tool, that is Z-transform. Z-transform is basically used to analyze signals and system that are discrete in nature. So specifically it will be used to solve difference equations, evaluate the response of LTI system, and also design or implement the digital systems. So you know that continuous time Fourier transform for continuous time aperiodic signal, and we use the discrete time Fourier transform for discrete time signals and systems. So in this lecture we'll develop the Z-transform representation of a sequence and study how the properties of the sequence are related to the properties of its Z-transform. So as we said on the previous slide, that Z-transform for discrete time signal is counterpart of the Laplace transform, which is used for the continuous time signals. Both Z-transform and Laplace transform have similar relationship to discrete time Fourier transform and continuous time Fourier transform respectively. So the advantages of Z-transform over the discrete time Fourier transform is that discrete time Fourier transform does not converge for all sequences, while Z-transform is the generalization of discrete time Fourier transform, which encompasses a broader class of signals. In analytical problems, the Z-transform notation is often more convenient than the discrete time Fourier transform notation. So the definition of the discrete time Fourier transform of a sequence is given by x of ej. You understand, you're well familiar with this notation, that e power j omega is basically the Fourier transform for the discrete time signals or response of the system. So we just sum it from n running from minus infinity up to infinity, and this is your x of n, and we multiply with e power minus j omega n, where omega is a real complex variable. You understand that the discrete time Fourier transform of a sequence itself is discrete, but its transform is continuous, right? That is, the x of ej omega is continuous. For the existence of the Fourier transform, it is required that this series or the discrete time signal should converge. So that means that it is absolutely summable, right? So if the sequence is absolutely summable, then we can find its Fourier transform, discrete time Fourier transform, or we can also say if it is not summable, then it must be square summable, right? Now, unfortunately, there are many signals that we would like to consider are not absolutely summable. So they do not have the discrete Fourier transform. For example, a step sequence is not absolutely summable. Also, the sequence mentioned here, that is 1 x of n equals to 1 by 2 power n u of minus n. So this is again not absolutely summable. Similarly, another sequence is sine of omega naught n. Again, if you sum it, absolutely sum it, and running from minus infinity up to infinity, so you'll find that it is also not absolutely summable. So as we'll see, that Z transforms allows us to deal with such a signals, meaning to say that those that are not absolutely summable, they still have the Z transform. Or if we talk about the system, so if the system impulse response is not absolutely summable, then the Fourier discrete time Fourier transform for that signal doesn't exist. But as far as Z transform is concerned, yes, we can have. So I mean, I'm talking about the unstable system, right? So Fourier discrete time Fourier transform is applicable to the stable LTI systems, right? But the Z transform can also be used for the case of the unstable systems. Z transform of a discrete time signal xn is defined as it is represented by x of z, and this is equal to summation n running from minus infinity up to infinity x of n z of e power minus n, where z is equal to r e power j omega. So because it's a complex, so that means we can also write it in rectangular form as real of z plus imaginary of z. But z is a complex variable. Thus x of z is a complex function of complex variable, unlike discrete time Fourier transform. We can also use the following notation which are normally used. So we represent it by the double arrow. So we say x of n double arrow of z equals to x of z. That means the inverse Z transform of x of z results into x of n, or the forward Z transform, that is of x of n will result into x of z. Or we also use the curly brackets and we say x of z equals to z of x of n. So these are different notations. Because z is a function of complex variable, it is convenient to describe it using a complex z plane. If you can recall the Laplace transform, so I think it will be easy for you to understand, right? In case of Laplace transform, we used a complex S-plane. So as shown in the figure, the axis of plane is illustrated in the figure, right? So that's your real of z, and this is your imaginary of z. So any arbitrary point z equals to r e j omega, and z plane is at a distance r from the origin. This is the origin, right? So that's the distance r from the origin, and at an angle omega. So here the variables are the two variables which are r and omega. So r can have values. R is a value between 0 and infinity, right? And similarly, the omega variable can have value between 0 and 2 pi. So if z equals to 1, then it is a circle of unit radius, referred to as unit circle. So when z equals to 1, at that point Z transform equals to the Fourier transform. Relationship with the Fourier transform. So I think you can clearly easily spot what the relationship between the Fourier transform and the Z transform is, right? So if we write z equals to r e power j, then we can say summation n running from minus infinity up to infinity x of n r e power j, and this is power minus n. So we can bring it together so that we can say that x of n multiplied by r e power j, r power minus n, and multiply by e power minus j omega n. So you see, if you multiply a signal with e power j omega n, that is the Fourier transform. So that means it's equal to the Fourier transform of a x of n multiplied by r power minus j. So we can say that the Z-transform is basically the Fourier transform of an exponentially weighted sequence, that is x of n multiplied by r power minus n. Now, as I said on previous slide, if r equals to 1, in that case r power 1 power minus n will result into 1. So putting this into this equation, we can see that this is basically Fourier transform. So that means, so I think you can easily observe that this is basically Fourier transform. Okay, because for the Fourier transform we have summation and running from minus infinity up to infinity, the sequence, and then multiply by e power minus j omega n. So that means when z absolute, which is r, right, when r equals to 1, in that case the z transform reduces to the discrete time Fourier transform. So we can say that x of z, which is z transform, when z equals to e power j omega, that means we are equating r equals to 1. We are taking the case when r equals to 1. So in that case, z transform and the discrete time Fourier transform are the same. So that means the unit circle in z plane corresponds to the Fourier discrete time Fourier transform. Or we can more specifically say that evaluating z transform at points around the unit circle beginning at z equals to 1, omega equals to 0, through z equals to j, right, omega equals to pi by 2, to the z equals to minus 1, when omega is pi, we obtain the values of x of j omega, which is the Fourier discrete time Fourier transform of the sequence from the values omega is equal to or greater than 0 to pi. So it's obvious that one would end up at the same point after one complete cycle, right? Because you start with this one, that's your unit circle. Okay, you start with here. Okay, start here, and then you move in these directions. Okay, and finally you reach at again this point. So you see that it also proves that Fourier transform is indeed periodic with period of 2 pi, because it has the same value at omega equals to 0 and at omega equals to 2 pi, right? So the Fourier transform is discrete time Fourier transform is periodic with period equal to 2 pi. So just like Fourier transform, Z transform is also a linear operator that transforms a signal from the time domain to a complex Z plane. The relationship between the time frequency, for the existence of the Z transform, the series in 3, which I have written here, that's written here, this one. Okay, must converge absolutely, right? So this must converge absolutely. So we can write it also like this. So this is your x of z, and we take the absolute value of this. So this is equal to, you see this one now, because we say z equals to r e power j omega, so I just write r e power j omega, right? And you know that r e power j omega, right? So the absolute value of the e j omega is always 1, that you know, right? So that means we exclude this one, we just straight away write x of n times r e power minus n absolute of this must be finite, or it must be less than infinity, right? So that means it will converge. Hence for the existence of Z-transform, the exponentially weighted sequence, that is x of n is a sequence, and this you have multiplied with it an exponential signal. So this should converge absolutely. So comparing it with the existence of the Fourier transform, in which we saw that the condition is in which we can see now that the condition is much relaxed. Hence there are many signals for which Fourier transform does not exist, but Z transform does exist. Secondly, note that the convergence depends only on the R, which is absolute value of Z, and it doesn't depend on Z itself. Then we have the region of convergence. I think you can recall from the Laplace also, we also discussed similar things. I mean, you have been taught similar things while you were doing in the course signal and system, where you were taught the Laplace transform, or maybe in any other mathematical subjects that you have taken so far, right? So the value of Z for which the series converges defines a region in the complex plane, and that is called the region of convergence, right? So region of convergence is a region in the complex plane and which shows the values of the Z. We'll see the ROC is an important, and anytime we cite x of z, we should also indicate the associated ROC, because for different signals we can have same mathematical expression as we had for the case of the Laplace, right? So different mathematical expression can result from same mathematical expression can result from different signals. So that means ROC is must, so that it makes it unique. So because the Z transform depends on the absolute value of Z, or we can straight away say that the value of R, in fact, then the ROC is also described in terms of absolute of Z. It is in general in the form of absolute of Z is equal to or greater than some variable A, and is less than or equal to some variable B, right? And they can have values between 0 and infinity. So let's have, before going into other topic, let's have some numerical examples, because you have just learned the definition of the Z transform. So let's use that definition and do some numerical problems. So I think I will leave it to you. I will just solve some of one of the example maybe. So let's take the first problem. I think you are maybe you are familiar with this, the curly bracket notation. In the curly bracket notation, we write the value of the signal, and the arrow indicates the starting point of the signal, that is 0, right? That is xn of 0 is indicated by the arrow. So for example, here it is pointing to the 1, so that means x of 0 has value 1, this is x of 1, this is x of 2, x3, 4, and so on. Similarly, if we look at this one, so in this case the starting point, that is n of 0 is this one, right? N equals to 0, so signal has value of 5 at n equals to 1. The signal has value of 7 at n equals to 2. Signal has value of 0 at n equals to 3, right? And similarly this one will be n equals to minus 1, so at n equals to minus 1, signal has value 4. N equals to minus 2, signal has value 2. So let's write the equation, right? First formula for the ZTransform. So we have x of z, and we can write it x of z equals to summation, right, and running from minus infinity up to infinity x of n, right, and z power minus n. Now because this is finite sequence, so we just straight away plug in the values. Okay, so this starts with 0. At n equals to 0 is a value 1, so we can straight away write just these values. So just okay, x of z, and this is equal to, I just start with n equals to 0, so x of 0 has value 1, so I straight away write 1, and because n is 0, so it will be z power minus, right, so z power 0 will be equal to 1, so 1 multiplied by 1 results into 1, plus then we have at this point for n equals to 1, so this is equal to 2, and when n equals to 1, then I can say that I can write 2 into z power minus 1 plus at n equals to 2 we have value 5, so I just write 5 into z power minus 2 plus at n equals to 3 we have value of 7, so I write 7 and z power minus 3 plus 0, right, and plus, so I think no need to write 0, we just straight away continue with it, so I just write plus, and then we have 1, so what position is this one? This is position number 5, right? So this position number 5 means at n equals to 5, so I write 1, so no need to write 1, straight away write z of minus 5, right? So I hope you understand, you can do in the similar way. So now if we look at the ROC for these, so ROC means region of convergence, so values of z where it will converge. So if we look at this one, z cannot have value of 0, because if z has value of 0 it will turn into infinity. Other than that, z so we can say the ROC for it will be the entire z plane, okay, and we say we can write it like z absolute must be greater than 0, because if z absolute is equal to 0, in that case putting 0 here will result into infinity. So I hope this gives you idea. I leave the rest of example to you, and I hope you can do them. Okay, I'll also leave the answers here. Let's take another example. Here we have x of n, which is equals to a power n u of n. You understand this signal is multiplied with u of n, which is a step function, and you know that step function is 1 only when its argument is equal to or greater than 0. So in this case the argument is n, so if n has values that is 0 or greater than 0, then this signal will be non-zero. So we can also represent it like this, that the signal equals to a power n when n is equal to greater than 0, and 0 when n is less than 0. Now to solve the to find the Z transform of this signal, we apply the equation 3, which says x of z equals to summation and running from minus infinity up to infinity x of n. But because in this case we have x of n equals to a of n u of n, so that means the signal has non-zero value from 0 up to infinity, so we can write it like this, a and z power minus n, and we can say that this is basically equal to, so multiplying the two, and because both have power n, so we take power n as common, so we can say that az minus 1 whole power n, right? So to I hope you know the equation that we use, the summing formula, which is okay. So we use this summation formula, which says that if you sum some number beta, and provided that beta absolute, right, you understand what is meaning of absolute, so beta absolute is less than 1, in that case this summation will result into 1 over 1 minus beta, right? So similarly, because this will converge only when a times z inverse should be less than 1. If it is equal to 1, you understand what will happen, right? This will diverge, right? Because if you sum 1 infinite time, it will result into 1, or for any other value, right? So that means it will converge only, right, when this term, the absolute value of this term is less than 1. Okay, so this will result into this, and as I said, it will be only applicable, right? If you understand, if and only if this thing, absolute value of this one is less than 1, or we can also write it as uh, uh, a absolute is less than absolute value of z. So all those values where this is satisfied is basically the region of convergence, right? Now we can write it like this, that x of n, which is equal to a of n u of n, its z transform will result into this mathematical expression, right? And its ROC will be this one, right? ROC means region of convergence, right? So for all values of where this equation is satisfied, this inequality is satisfied, is called the region of convergence, right? You understand, if z absolute is equal to a, or if z absolute is less than 1, in that case this summation will not result into some finite value, it will result into infinity, which we call the divergence. So this expression will converge only if this condition is satisfied. I hope all the things are clear to you. So we can say that basically the ROC of this one is this relationship. Now if a of absolute a of z is equal to absolute of a describes a circle of radius a, right? So at the origin in the complex z plane, this is your complex z plane, right? So the region of convergence will be all those values where this absolute of z is greater than absolute of a. So this corresponds to the exterior of the circle of radius a, right? So that's a circle, right? And it has a radius of a. You understand, distance from here to here are as indicated here, right? So this is a circle of a. So the region of convergence will be all those points that are exterior of this, right, circle of radius a. So hope this gives you the idea. So let's take another example. In this example, we have the uh, value of x of n equals to minus a power n u of minus n minus 1, right? You understand, we also call the step function as a switch, right? So the signal has its value when the switch is on. So when it is on, you understand, it will be on only when its argument, which in this case is this one, if this argument, right, if this is equal to or greater than 0. So only in this condition it will be we will have the value of the signal. If this condition is not satisfied, that means the argument of this one is less than 0. In that case, the step will be 0, and you know anything multiplied by 0 will result into 0. So when will be the argument of this one greater than 0? So minus 1 minus n minus 1 should be greater than 0. Okay, so that means, so this condition is satisfied when n is equal to or less than minus 1, right? So that means this signal exists for all values where n is less than or equal to minus 1. So let's apply the equation. So because originally in the equation we sum it from minus infinity up to infinity, right? So in this case, because n cannot be greater than minus 1, so that means we will sum it from n running from minus infinity up to minus 1, and we write the signal minus a of n z of minus n. So that means we take minus as common and we write straight away, right? And also we change the variable of summation, right? So if I replace n with minus m, so that means this minus infinity will become plus infinity, this minus 1 will become plus 1, and this power minus 1, right? Because we can write it as this as a of, right, a into, right, minus 1 and this whole. So I hope you understand, right? Because if you look at this one, this is a n z power minus 1. So if I just write it minus 1, so if I can write it as n minus n, right? So if I remove the bracket again, so minus 1 into minus n, it will become a power n and z power minus n. So I hope you understand this small mathematical trick to make things easier. Okay, so now we have m running from minus infinity up to infinity, and we have this form. Okay, so again summing it, this one with the assumption that a inverse of z, right, this is the absolute value of this one, is less than 1. So if this is the case, then it will converge, otherwise it will not converge, right? So using the summing equation, let me rewrite, right? So this is the summation equation, and which says if beta absolute is less than 1, in that case, if you have some limit k running from L up to infinity, beta power k, this will result into beta power L upon 1 minus beta, and we with the assumption that beta absolute is less than 1. Now looking at here, we have m running from 1 up to infinity, and this is your beta, right? So a inverse of z, this is your beta. So because m running from 1, so instead of L we will have 1, so minus 1, right? Minus is already there, right? This one, okay, this one. So we can write it minus 1 minus a inverse of z upon 1 minus a inverse of z, and provided that absolute value of a inverse of z must be less than 1. So that means the region of convergence for this will be z. So the region of convergence, you understand, a absolute, right, a power minus 1. So if I bring it to this side, I'll get something like z absolute should be less than absolute of a, right? Or I can also write it this expression in this format, right? And how I get, I simply say, okay, let me write. Okay, so a inverse of z can be written as a, or sorry, it will be z over a, right? Right. So a inverse of z can be written as z over a. So that means this is basically z over a divided by 1 minus a inverse of z. So z over a can be brought here, so that becomes a division, you understand. So we have minus 1 over 1 minus z inverse, a inverse z over a, right? So on simplification, this will become minus 1, and this will become, you see, z over a is basically a over z, so it will be a over z, right? And minus a inverse of z into a over z. So that means this z cancels with this one. This is a inverse and this is a, so they cancel. I get 1 here, right? So if I take minus 1 common, then this minus 1 will become plus 1. It will come here, and the minus 1 and the one I have taken common will cancel, and I will get this expression. Right, so the Z transform for this one, and you can see in the previous case we get the similar expression for the two different signals. You see, this one is anti-causal signal, and the previous one that's also called the left-sided signal, and in the previous example it was the causal signal or the right-sided signal, and we get the same mathematical expression, right? If you go back to the previous slide, so you'll see that they both are actually same, but the region of convergence for both are different. In the previous case, the region of convergence was outside the circle, and the circle had radius of a. In previous case, it was absolute of a was less than absolute of z, and that was the region of convergence. But in this case, the region of convergence is opposite what we had in the previous case, so it is absolute of z is less than this. So that's your circle with radius a, so region of convergence is inside of it. So that means we can say Z transform is only unique if we have the ROC also, because two different signal can result into same mathematical expression. So I think that's all for this numerical. I hope you understand that two different mathematical expression two same mathematical expression are from two different signals. So again, we have another signal that has value equals to b of n u of n minus 1 plus a of n u of n, right? So that you understand, because we are multiplying the step signals here. So step signal is a mathematical switch. So for the first part, it is basically, it will be equal to b of n for all values where n is less than 0, or we can also say when n is less than or equal to minus 1. Okay, and the value u a of n when n is equal to or greater than 0. So to find the expression for this one, again the equation says that you sum the x of n from minus infinity up to infinity, and you multiply it with z power minus n. But in this case, we have two separate two-sided sequence that are infinite in duration, right? So for the left side, that sequence is from minus infinity up to minus 1, and its value is equal to b of n. Similarly, plus the right-sided sequence is from n running from 0 up to infinity, and this one. So I hope you can find the summation, because we have done similar problem, right? The previous example, so you can find the mathematical expression for this, and you understand that. So we have region of convergence for the first part, that is this one, or the z should be greater than z should be less than absolute of b. You understand, right? B inverse z should be absolute of this one should be greater less than minus 1. So that means if I bring b inverse this side, it will become b. So absolute of z should be less than absolute of b, as indicated here. For the second part, we can say Z inverse. So if I bring it here, then A absolute is less than absolute of Z, or we can say the absolute of Z should always be greater than this. So the overall region of convergence for this one will be the ending of the two region of convergence, right? So for the left-sided sequence, this is region of convergence, right? And for the right-sided sequence, this is the region of convergence, right? So the x of z will converge only when both the series converges, that is the left-sided one and the right-sided one. Thus the ROC is the intersection of both of the regions specified by this one, right? So that is this one, the left-sided sequence and the right-sided sequence, right? So that means the region of convergence will be when z is greater than absolute of a and it is less than absolute of b. So in this the signal will only converge for this region, right? So you can understand now the ROC will be annular, or you can also say a ring, right, shaped region in a complex Z plane as shown in the figure above. Also we must have this relationship, that is absolute of B should be greater than absolute of A for x of Z to exist. Otherwise two rocks do not overlap and their intersection is a null set. So that means there will be no region of convergence, so no Z transform will exist. So with this we end the lecture for today, and see we'll start the next lecture from this slide. But meanwhile, this is your homework. You have x of n equals to 1 over 2 to the power n u of n plus minus 1 over 3 to the power n u of n. This is your homework, and this is the answer for the homework, and this the mathematical expression, and this one is the region of convergence value, right? That is, for this particular case, absolute of z must be greater than 1 by 2. Only then this will the Fourier the Z transform will converge. Okay, see you in the live session. Allah Hafiz.